Okay, first problem. First problem says, use the equation below to estimate the number of crystal-like clusters in a 1 cubic millimeter of copper at the melting temperature for a 10 and a 60 atom cluster. So that's kind of the first part, and then the second is approximate the clusters to be, to do this, we approximate them to be spherical, which, is not exactly right, because 10 atoms is small, but it's a reasonable first approximation. What volume of liquid is likely to contain one cluster of 100 atoms, which is just an extension of these. It's the same problem, essentially. You're given the atomic volume of liquid copper and the solid liquid interface energy, and the Boltzmann constant, and the melting temperature. And then here are the two equations. So basically, we're interested in the number of clusters of that size. N0, so N0, that's going to be atoms per cubic millimeter, right? But to do that, we have to use 1 atom per 1.6 times 10 to the minus 29 cubic meter, right? Because you have the volume of liquid copper. So that gives you the volume of liquid copper in atom per cubic meter times 1 cubic meter per 1 times 10 to the 3 cube millimeter cubed. So that gives us N0. Also in this, we have the Boltzmann constant, and we have the temperature because this is at the melting temperature. T equals Tm equals 1356 K. Okay? We need to know delta G as a function of R, which we have this equation for. And in that equation, we have negative 4/3 pi r cubed delta GV plus 4 pi r squared gamma SL. Well, we're at T melting, which means this term, delta GV, is 0, right? Because the thermodynamic driving force is 0. We have to undercool it in order to get delta GV that's not 0. Which means now that we can write NR is equal to N0 x negative 4 pi r squared gamma SL, okay, over KBT M. So for this, we know gamma SL is 0.177 joule per meter cubed, or sorry, per meter square. We have the Boltzmann constant, and basically we have everything we need for that. So the next question is, what is R? And R, if we assume spherical, assume a spherical cluster, then we have 4/3 pi r cubed is equal to n number of atoms in the cluster times omega. So this is number of atoms. This is going to be volume per atom. And a piece of paper. So basically we can write now NR is equal to N0, which is 1 over 1.6 times 10 to the, let's write this out. It's bigger. R is equal to 1 over 1.6 times 10 to the negative 29 times 1 times 10 to the 3 raised to the 3, 9, is N0, exp negative 4 pi, and then r squared here, this is going to be n atom omega over 4/3 pi cubed is r. So then r is going to be n atom, and volume per atom is 1.6 times 10 to the minus 29 meters cubed times thousand cubed omega over 4/3 pi third 2/3 over Boltzmann is 1.38 times 10 to the negative 23 joule per K times the melting temperature, which is 1356 K. Okay, so here we have an expression for the NR as a function of number of atoms. So using an atom equals 10, we get n equals 9 times 10 to the 13 cluster per cubic meter, and substituting in n atom equals 60, n is equal to 3 cluster per cubic millimeter, and n atom equals 100 gives us n is equal to 4 times 10 to the minus 8 cluster per cubic millimeter. And the way the problem was worded is asking for the volume of liquid likely to contain one cluster. So this last part for n atom equals 100, we can rewrite that as 25 cubic meters per cluster So I took this and I inverted it and converted it from millimeter to meter, because it's 10 to the minus 8, which is a pretty small number. And that's solving the problem.